close enough. All right, so the last talk in the session is going to be on a different topic. So this is about inhabitation in the context of quantitative types. And it's going to be presented by Giulio.
Thank you very much. And thanks for the introduction. Thank you everyone for being here. I'll be presenting quantitative inhabitation for different Lambda Calculi in the Unifying framework. So also sorry for that long title. I'll spend the first 10 minutes trying to explain the words composing it and then how we solve it. And this is a joint work with my PhD advisors, Giulio, Guerrieri, and Delia. So, in order to talk about inhabitation, let me first present what it is. And to do so, let's start with a well-known problem, which is the typing problem, stated as follows. If someone gives you a program T, are you able to say if there exists a typing context gamma and a type sigma that can be used to type it? And if you are able to answer such a question, you're gaining knowledge on how to build typers and ensure that your program runs along. So it's really important, and this problem is built around the interaction of the typing system with the time system. But we could look at the dual question, which is the inhabitation problem. And it is built the opposite way. This time someone gives you the typing context gamma and the type sigma and asks you, does it exist a program T that can be used in such typing? And if you are capable of answering such question, you are potentially doing a very basic form of program synthesis, since they give you some sort of specification for the typing, and you answer with a program that meets that specification. And from a more logical point of view, through the career-wide isomorphism, you are doing proof search, since the typing corresponds to formula in the typing. So that is the problem to study here. And the goal is to do streets for different lambda calculi. So it is well known that we have different models of computation. The two most common one will be called by name, where when we have a regex, we substitute inside it and have a compute in the arguments. And oppositely for call by value, we compute the argument to a value and then substitute it. And the goal is to study inhabitation for these two calculus in a unifying way. So we need a unifying framework to study them together, and there exists multiple frameworks to do so. There's a well-known callback push value, but we decided to work in what's called distant bind calculus. Well, for now, bind calculus, which is, to our knowledge, like callback push value like language, and I'll try to take the following minutes to convince you that it is. So first, let's start with the syntax to try to see how it's built. It is built out of the usual lambda calculus, but there are two new constructors. A first one called bind, which introduces values, and a second one called there, which introduces computation. So these two new constructors are syntactical means of playing with values and computation. And it happens that the calculus works better with what's called distance, so we have to introduce lag constructs inside of it, but it's not important here. So that was for syntax, and we have syntactical means of representing values and computation, and playing with them, we are able to build what we are. Then we're able to build a subsuming pattern in the following sense. We have, by placing the bang interlection at the right places, we're able to build an embedding of call by name inside bang. And this embedding has sweet properties, being, for example, that we can express side properties in the call by name through the corresponding one in bang. For example, a time T in call by name is normal form if and only if its embedding is a normal form in bang. So we are preserving the property in bang. And this is also true for dynamic properties like reduction that can be expressed with equivalently with the corresponding notion in bang. This also works for call by value with the corresponding embedding. And in that sense, we consider that it is a like callback push value like language. And the question we had is, can we do the same thing for inhabitation? Can it be preserved through the embedding? And so that was for this, and now we have to talk about the quantitative aspect of our work. So, okay, in order to do inhabitation, we need types, and the most common one might be simple types. And what we have with them is that the set of typable terms is strictly contained in the set of terminating ones. So we are ensuring termination, but it also means that there are terminating terms which are not typable. And we might want to work with them too. So a solution might be to increase the typing system with a new construct, which are finite collections of terms, also called intersections. And when we do this, what we have is that the set of typable terms exactly meets the set of terminating ones. So we are characterizing termination, which is quite interesting. But we have this finite collection, we need to choose which type of collection we are. So it's quite natural to take associativity and non-idempotency on them. However, there is a question about idempotency. And both choices give interesting results, but with different strength. If we take an idempotent intersection type system, so it's in a way working with a set of types, what we have is a qualitative system, meaning that we're characterizing termination, but we can't say much more than this. What is interesting is that when we take a non-idempotent intersection type system, there's something much stronger, which are quantitative properties. It means that from the typing, we can extract measures on the dynamic aspect of a program. For example, we can extract the length of the reduction to the normal form, as well as the size of the normal form. So this is quite interesting, and this might be the first reason why we'll be working with non-idempotent intersection type. And the second one being the already known results about typability and inhabitation for intersection type system. So let's quickly compare the two problems and known results for these types. What we have is that for simple type, the typing is decidable. However, for intersection type, it is undecidable because we're characterizing termination. So we definitely can't decide it. What's interesting is to see what happens for inhabitation. For simple type, it is decidable, but it has been shown that for idempotent intersection type, it is undecidable. Strangely, when we take non-idempotent intersection types, it has been shown that for co-binding, the problem become again decidable. And that is why we'll look at this settings to try to see if it is true also in the band. And one corollary of our work is that it is decidable also for co-binding. Okay, so practically speaking, what does it mean? And what are we working with? So we're working with three typing systems, one for call-by name, one for call-by value, and one for bind. And since we're using a subsuming padding, what's interesting is that the typing properties are also preserved. In the following sense, if we place ourselves in call-by name and take a program, it is typable with typing gamma sigma, if and only if, for the corresponding notion, it is typable with the same context and type in line. So we are strongly preserving typing. And the same thing happens for call-by value with the corresponding typing system. So this tells us that things may work well with inhabitation. And so that's the idea. I hope that we'll explain everything. We can have a look on how it works and how we solve it. All right. So the first goal might be to decide the inhabitation problem for BAM. Since we've seen that things work well with the typing system, an idea could be to also decide the inhabitation problem for call-by name and call-by value using the solution for BAM. Try to minimize the proof. But in fact, we can be more ambitious than this. We can try to find all solutions to the inhabitation problem for given gamma sigma, and try to recover all of them for call-by value and call-by name, and try to do this in as generic way as possible, so that if other embedding are introduced, we may also use this work to decide inhabitation for them. So these are our three goals we are trying to solve. So we we don't just want one solution, we want all solutions for given gamma sigma. The problem is the set of solutions is either infinite or unlimited. This is simple to see. If there's one solution, we have separate reduction, and put the identity in front of it, we have another solution. So either we don't have solution or infinitely many. So we can't really try to find all solutions. So what we will do is try to find a finite generator of a set of solutions. So a finite set of terms from which we can regenerate the whole set of solutions. And this generator, that we call a basis, we want it to be correct and complete in the following sense that if we span it, we exactly get the set of solutions, but the span operation has to be something very simple. We can't cheat by hiding things in the span. There has to be something like regex expansion, but nothing much more than this. And first result is that in Bang, such a basis exists, is finite, correct, and complete. And to build the basis, we're using, for those who know about it, the bone approximation. And we're choosing some approximates to build the basis. And so now that we have the basis, we can try to seek for it using an algorithm. So how do we do it? Well, the inhabitation problem is a typing problem, so we will try to rebuild all type entries, but only on elements of the basis, since we know that they are finitely mediable. So we have to follow two sets of rules, the typing rules, to only build solution, and some grammar restriction. Because what is interesting is that the union of all bases is forming, can be characterized by a tree grammar. So by synchronizing them, we are able to always stay in this intersection, this sweet spot, and we are able to build an algorithm which will show elements and compute the basis. Practically speaking, it looks like this. It's pretty much awful. But let's quickly look at one rule to see what happens. So let's take the application rule, and when we zoom on it, what we see is that we have elements which corresponds to an application typing rule. We have also elements which corresponds to the building of an application in a grammar rule. And the idea is that we synchronize them. We tweak some type thing to try to find the missing ones. And we build all the rules of the algorithm this way. If you're scared of playing with it, the good thing is it has been implemented, so you can always go on GitHub and play with it. What are the properties of such an algorithm? Well, it is naturally non-deterministic. Because of this rule presentation, we have to try to build all trees out of it. And some elements of the rule are also non-deterministic. So it has been quite hard to show that with terminates, but we did it. And we've shown that it has a finite, each non-deterministic rank terminates, and there is finitely many of them. So we can always non-deterministically simulate the algorithm, and that's what the implementation does. And it is some and complete in the sense that it exactly founds the basis we want. And so this solves our first problem. Now the question is, how can we do this in others? Well, when we look at combining, we can always apply the standard methodology, which was already done, try to find the basis, finite correct complete, and build an algorithm finding it. But again, we have to prove that this algorithm is correct, complete, terminates, and it's a lot of work. So we can try to use the Bang algorithm to find again that basis. And this is possible through a central property, which is that the basis is also preserved by the embedded. So if we look at this diagram, typically what it means is that when we draw the two words, the corresponding basis for a given gamma and sigma, and the basis for combining is sent as a subset of the basis for Bang. And since we have an algorithm capable of computing that basis, we're using it, then we're discarding the solution which are not ones in the form of an embedded term, and then we're decoding to get back the basis in combining. And in fact, we can be smarter than this. Instead of computing all solutions and then discard them, since the algorithm is driven by a grammar, we can restrict the grammar to only find the subset we're interested in. And then, using the decoding function, we're able to get the full basis. For Cobra values and question, we've shown that the basis exists, is finite, right, and complete, and we can build an algorithm to build it. This time, it's much harder than binary, so we absolutely don't want to prove again that this is correct, complete, and all of this. So again, we are trying to solve this through, and what a chance, the basis is preserved again. A program is in the basis in global value if and only if it's embedding into the basis. Diagrammatically, we have the same picture with the basis, which is embedded in the basis. Again, we can use the Fang algorithm to compute the full set of solutions. And then discard the solution which are not in the form of embedded terms. Use the decoding function, and we've decided the inhabitation problem. Again, instead of discarding them, we can restrict the grammar to only find the subsets inside of it, and use the decoding function, so we've limited the work that we're doing. What are the properties of this algorithm? Well, we knew that the Bang algorithm terminated was correct and complete. And this helped us solve the first goal. And since our algorithm only uses the Bang algorithm and the translation, naturally, this terminates. And using the correctness and completeness of basis, we're keeping correctness and completeness of the algorithm. One thing is the restriction of grammar may break completeness. But we've shown that in the case of combining and compa value, it doesn't work. And in particular, what's interesting, so this solves 1, 2, but what is interesting is that this restriction preserves soundness and completeness for a general set of grammar. So this could be done for other embeddings. And so this means that when you were trying to solve inhabitation in closed framework, you can always try to reduce that problem to the Bang one. And so this solves our last goal. And it comes with the implementation, so you can play with the combining and compa value indirect algorithm, and you can even build a subset of a grammar if you want to target over specific subsets. So that was it. So we solved the generalized inhabitation problem, finding all solutions through a finite basis in a very generic way for multiple models of computation with the corresponding implementation. And what do we want to do now? Well, we would like to look at solvability in a similar way. What is solvability? Is trying to, in a way, find the program which has a minimal computational meaning that we can extract. And it happens that in the characterization of solvability in closed languages, inhabitation appears. So this might help us. And another thing we have is that the inhabitation for Lambda Calculus with pattern matching was not as strong as this result, and it happens that this result can also be applied to this sort of languages. So we have strengthened inhabitation in that case. Thank you for your attention, and please ask any questions.
So we have plenty of time for questions.
Giulio from Paris. So in your basis, all terms are normal approximate, right? So I'd like to understand that from this you can really generate all typable terms, even the non-normal ones?
The span operation is built out of reduction extension. So this solves the case of a non-normal one, and then term plugging for the constant model, which have been introduced because of approximation. But we can show that, so maybe it have already been shown for combined name, but it happens that it also works for combined value. We're not losing completeness just by doing these two operations. We're still exactly spanning the full set of solutions.
I'm Ugo Dell'Anno from Bologna. So I was wondering about the complexity of your algorithm and about the complexity of the problem. Is there any lower bound?
We haven't looked at it yet. It might be linked to, one of the applications of this could be to generate lambda terms, but in a unified way, in a like probabilistically distributed way. And I think looking at the complexity might use the same tool as this, and we haven't had time yet to look at this. But it could be interesting. Right now, the complexity is definitely not good, but it depends on the size of the type, and so usually the types are really small. So I never crashed the implementation because of this. But I think it would be interesting to look at it, yes.
Giulio from the University of Hong Kong. I'm wondering, is the decoding process from the bank to programming molecular value a challenge, or is it just straightforward?
No, it's really simple because there is a small tweak for global value, but you pretty much just need to erase the bang and there, and that's all. So it's very simple. It could be trickier to check that your program is indeed an embedded program. So, but to do this is just syntactical work. If it has the right shape, then it's okay, and if not, then you destroy it. So, all over is not the hardest part.
Thank you.
Okay, so if there are any more questions, then you should thank the speaker.